Okay, so we seem to have quite a few people who are stuck. So let's just make our way through things. First off, proving the second to last term in each row is equal to the row number. When it comes to our Pascal's triangle, as we look at the rows, the second to last term in every row always has its R value one smaller than its N. That's why it is this. That's why we're technically trying to prove that n combinations of n minus 1 is equal to n. To do this, we have our combinations formula. N combinations of r is equal to n factorial over n minus r factorial, r factorial. N combinations of n minus 1. N stayed n, r became n minus 1. So that's n factorial over n minus. Now when you substitute things in, technically you put them in parentheses. It's not always necessary, but in situations where you're subtracting things, it's necessary. So when I plug in n minus 1, it needs to go in its own parenthesis, both there and here. And from here, I'm doing some algebra to simplify things down, like distributing my negative. N factorial over n minus n plus 1 factorial. I can't distribute factorials, but that wasn't the factorial. That was the negative inside parentheses. What's going to happen to the n minus n? Cancels. I've got n factorial over 1 factorial n minus 1 factorial. And what is 1 factorial? 1. N factorial is currently over n minus 1 factorial. Here's where most people get stuck. You have to expand out your factorials. A factorial means to multiply something by all numbers smaller than it. Assuming n is a whole number, it has to be to do it in combinations and permutations. N factorial is n times what number is 1 smaller than n? N minus 1. What number is 1 smaller than that? N minus 2. I could keep going. When do factorials stop? 1. Now I've got n minus 1 factorial. It starts at n minus 1 and then multiplies by every number smaller than it. What's smaller than n minus 1? N minus 2. I could keep writing them out. I'm not going to because I know they stop at 1. What's going to happen in my fraction? It gets cancel happy. And the only thing I'm left with is n. I'm going to do homework questions after notes today just because of the fact that I already started the warm-up. And I want to keep going with our notes. Between yesterday's notes, today's warm-up, and yesterday's assignment, we've done 4 proofs. When it comes to Pascal's triangle, there are a total of 4 proofs. We've done them all. This is the hardest one. The ones on your homework yesterday were the 2 easiest ones. So, those are the only 4 proofs that are in Pascal's triangle. We've seen them all. Second half of the warm-up. Expand the following. To expand a binomial to a power means to actually go through and multiply it out. I start with this one for a reason. X plus y to the first power is just x plus y. Because putting something to the first power just means it's there once. What does it mean to square something? Times it by itself. This is x plus y getting multiplied by x plus y. But the actual expansion has it all FOILed out. X times x. X times y. Y times x. And y times y. After I combine like terms, I get x squared plus 2xy plus y squared. To cube something is to multiply it by itself. 3 times. How do you multiply 3 things together? Two at a time, and you're going to have to distribute twice. Hey, I already know that x plus y times x plus y is x squared plus 2xy plus y squared. I did it on the previous problem. Has to get multiplied by the x plus y. X cubed plus x squared y plus 2x squared y plus 2xy squared plus xy squared plus y cubed. After combining like terms, it'll look like x cubed plus 3x squared y plus 3xy squared plus y cubed. How many of you are wondering why the heck we're all of a sudden multiplying out binomials? Anyone? Seems a little out of place, doesn't it? After doing Pascal's triangle and sequences and series for so long, it seems a little odd. There's a reason for it. I want to look at the coefficients that are on these problems. Y'all know what a coefficient is? It's the numbers in front of variables. What are the coefficients in my first term, or in my first expansion? 1 and 1. What about this one? 1, then 2, then 1. And our last one? 1, 3, 3, 1. Does that look familiar? Pascal's triangle. Row 1, row 2, and row 3. Pascal's triangle's biggest use is in expanding binomials to a power. That's why you're seeing this today, and that's what we're getting into today, is how to use Pascal's triangle to help us out. .6, day 1. I forgot to write day 1. 10.6 is all about binomial theorem. The binomial theorem is a theorem that is used to expand binomials to some power. Binomials are polynomials in two terms. So there's two pieces. And when I put them to a power, it can get really tedious really quick. So let's say I have the binomial. It's going to start with a plus b, but a and b are placeholders for numbers and variables. And I'm going to put it to the power of some n. So the first power is easy. Squared, not too terrible. Cubed gets a little more tedious. But if I were to put something to the power of 8, that would really suck. So this is where this theorem comes in. It's almost like it has something to do with sequences and series. Binomial theorem is the series from k equals 0 to n of n combinations of k getting multiplied by a to the power of n minus k getting multiplied by b to the power of k. This is a really ugly formula that we do not use. Because you should see it. And because I give you the actual formula to kind of break down what it is that we're doing, to explain where the things are coming from. So, series means I'm doing what to a bunch of things? I'm adding them all together. I'm going to add together a bunch of terms. What's this? Combinations. N combinations of k. Now, n is a set number. But k in a series where k is the variable that changes, k is going to keep changing. It's going to start at 0 and it's going to get bigger and bigger and bigger and bigger until it reaches whatever n is. So that means I'm going to have things like n combinations of 0, followed by n combinations of 1, followed by n combinations of 2, followed by n combinations of 3. And I'm going to keep going until I get to n combinations of n. Where have we seen a pattern of combinations where it just increases by 1 in the r value before? Pascal's triangle. So this piece tells us to do Pascal's triangle. Because Pascal's triangle has already done all the combinations for us. It saves us the extra math. And then this a to the power of n minus k, if k starts off as 0, that's going to start with a to the power of n. A is the first term of the binomial. It's going to start off to the power that's on the binomial. And then as we go from term to term, as k gets bigger, that results in that power is going to get smaller. The second term, the b, starts to the power of k, is going to start to the power of 0. And as we go from term to term, the exponent's going to get bigger. So, that means we can do things like this. Without having to write out x plus 3 times 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 x plus 3, and foiling and distributing for the rest of our lives to make that happen. So, things we have to pay attention to. In the binomial theorem, the power that's on the binomial is n. N is the first number in the combination. The first number in the combination tells you where to look at Pascal's triangle. Now, talking about this and this again. The first term, in this case, our first term in our binomial was just x. Its powers are going to start off at, in this case, 6, because that's the exponent, and decrease each term. Specifically, decrease by 1, because as you go through a series, k, this variable increases by 1 every time, and as that increases by 1, this decreases by 1, because it's subtracting it. Our second term, in this case, is just a 3. Its power will start at 0. And increases each term. So that's the breakdown of what is going to do what. Let's do the actual expansion. General pattern that I follow. Pascal's number, first term, second term, plus. Pascal's triangle, first term, second term, plus. Pascal's triangle, first term, second term, plus. You get the picture? Okay. One thing that can be helpful so that you can cross things off is actually write down Pascal's sixth row. Do you have to? No. Does it help people? Often. Goes 1, 6, 15, 20, 15, 6, 1. X plus 3 to the power of 6 equals. I grab the first number off of Pascal's row. 1. When I use it, I cross it off so I make sure I don't try to use it again. I take the first term, whatever it is. I put it in parentheses. There's a reason for that. We'll talk about that. And the first term goes to its power, that's whatever, right here. I also take the second term and put it to the power of 0. Keep in mind, these things are all being multiplied together. After I get all those 3 pieces, I repeat what I'm looking for. The next number from Pascal's row, cross it off so I don't use it again. The first term, its power must now decrease by 1. It was to the power of 6 on the previous problem, now it is to the power of 5. The second term, the 3 in this case, its power is going to increase. It was to the power of 0, now it is to the power of 1. I repeat this process until I get to the end of Pascal's row. Because if you expand something to the 6th power, it should have 7 total terms. Pascal's triangle has 7 numbers in it in the 6th row. 15. X is now to the power of 4, and 3 is to the power of 2. Pascal's number is now 20. X is to what power?
30.
3. 3 is to the power of? Also 3. 15. X is now to the power of 2, and 3 is to the power of? More than just one person in this room can add 1. Power was 3, it's now 4 plus 6. X to the power of 1, 3 to the power of 5, plus 1, x to the power of 0, 3 to the power of 6. Now, many of you are probably thinking right now this is a lot of writing. It is a lot less writing than if I had to actual FOIL out the x plus 3 6 times. From here, we simplify what we can. I start with 0 powers. What's anything to the power of 0? 1. Do I really need times 1? Because they're all being multiplied by things. No. That's essentially gone. That's essentially gone. Those are both to the power of 0. 1 gets multiplied by x to the power of 6. If there was more than one thing in that parenthesis, that 6 would have to go on both of them. There's not. So, the first term just simplifies to x to the 6th power. Second term. Make sure you follow order of operations. Exponents go first. What is 3 to the 1st power? 3. 3 times 6 is 18. That's the only numbers involved in that problem. And then there's x to the power of 5 left. Now, you can go through term by term and do the math in your head, or you could just put the numbers into the calculator. 15 is getting multiplied by 3 squared. 135. X to what power is on that term? To the 4th. Move on to the next one. 20 is getting multiplied by 3 to the power of 3. 540. X was cubed. 15 was getting multiplied by 3 to the power of 4. 1,215. X was to the power of 2 on that term. 6 was getting multiplied by 3 to the 5th power. 1458. X was to the 1st power. In other words, it was just x. And the last term was 1 getting multiplied by 3 to the 6th. 729. In other words, x is canceled out on that one. Binomial theorem can be a lot of writing. I understand that. As the powers get bigger, it's more writing. But it's still a heck of a lot less writing than if we had to multiply all 6 of them out. Binomial theorem is hugely helpful as we are simplifying things to higher powers. Comes up a lot in higher order math classes. I have one more example for you. Two x minus 4 to the power of 3. I know I'm going to use Pascal's triangle because I have a binomial to a power. Carly, which row of Pascal's triangle am I looking at? Kylie, Greener. What numbers are in the third row of Pascal's triangle? Mm-hmm. Now, as I do this, Pascal's number goes first. 1. When you are doing the A and the B, when you are putting things to the powers, you got to make sure that you put the entirety of A and the entirety of B to that power. Because the original structure is A plus B. That means the A in this situation is the 2x. And the B in this situation is -4. So be careful with that. First term, 2x. Adela, what power should I put that first term to? 3. I also have the second term involved. Liam, what power should I put that to? 0. Yes. In between terms is always plus. Braylon, how do I start the next thing? The 3 from Pascal's triangle. Ruby, what goes with that 3? 2x squared, and you could stop right there if you would like. Aubrey, what else goes with it?
The -4 to the first power.
-4 is to the first power. Ellie, what comes next? +3. We're going back from here. What's the first piece of what goes with that 3, Veda? To what power? 1. Good. Miriam, what else goes with that? -4 squared. Isaiah, what about on the last one? +1. Burton, what's the first part of what goes with it? 2x. And Jack, what's the last piece? -4 to the power of 3. I start simplifying. First thing I simplify is anything to the power of 0. Lenora, why? What's anything to the power of 0? 1. And it's all being multiplied by things. Do we ever actually need to multiply by 1? No. 0 power, 0 power. If you choose not to write those pieces, it's not the end of the world. Just be careful and make sure you don't accidentally miss pieces later. I simplify things down. Be careful. As I'm simplifying things down right here, it does not start with 2, because 2 is to what power? 3. That power goes on all the pieces. So it's 1 times 2 cubed. The 1 doesn't do anything, but 2 to the power of 3 is 8. X is also to the power of 3. Austin, what would the second term look like? Plus what? I've got numbers in all of these. This is where a calculator comes into play. No. All of these are being multiplied. So I go to my calculator, I type in 3, I type in parentheses 2 to the power of 2, and in parentheses negative 4 to the power of 1. The coefficient on the next term is a negative 48. So minus 48. Austin, I'm going back to you. X to what power? Yes. Sam. Third term, what number? While he's typing that in, Alex, what's your question? How'd I get negative 48? 3, 2 squared, and negative 4 to the first, all multiplied in my calculator. Sam, you get the next one? No. Know the answer. I just knew negative 24 was not close. Yeah, 96. What did you say, positive or negative? Positive. Beautiful. Hannah, what's the last one? She didn't see it, but pretty much. Negative 64. Do you notice that it goes back and forth from positive to negative on this one? Does it make sense that it would do that? Because the negative 4 starts out at an even power, then goes to an odd power, then goes to an even power, then goes to an odd power. Negatives to even powers are always positive, but negatives to odd powers are always negative. When there is a minus, it should go back and forth positive and negative. If it doesn't, you've done something wrong. It's not nonsense, it's tedious. Tedious does not make nonsense.